So let's get into chapter 4. This is bioenergy. Pick up a couple of the figures. Look through those guys. It's one of the longer chapters in the book. Okay, so this little cartoon more or less shows the flow of energy through organic systems. We spent the first 3 weeks basically looking at the first couple weeks looking at the flows of energy through the earth. This is just now looking right down in what flows through biological systems. And back a couple chapters ago, we saw what the total amount was. The photosynthesis efficiency is actually relatively small. I don't know if we're going to get to it today or not, but there's a problem here in the book. Kind of shows the energy losses all along the way. But what we can see there, and what they're not showing, well, I guess they're kind of labeling it. Photosynthesis just basically means taking the photon energy from the light that goes through the photosynthetic pathway. I love showing this other picture. I can't help but show this. Photosystem 1. I might have mentioned to you a couple days ago, I had a philosophy professor, and he and I were talking about why you don't hear a whole heck of a lot more about nanotechnology. We did talk at length last couple of weeks about what goes into making a PV panel. So you get your pure silicon, you dope it with some phosphorus, you dope it with some boron. You might have a fancy germanium panel, different wavelengths, more expensive, et cetera, et cetera. This is how nature does it. We have not figured out how to build one of these yet, but this is the actual protein complex that takes photons and converts that photon energy more or less into electrical energy. It takes an electron, bumps it up into a higher state, not unlike what we studied with the PV. Once that electron's kicking around, it can then become active in synthesizing larger molecules. So that electron actually goes into the synthesis of glucose, starches, cellulose, what have you. But that's your bio nanotech right there, photosystem 1. And there are plenty of other examples. Here's kind of a cartoon depiction, but once that light comes in, you have all kinds of other biochemistry going on. So that's basically what happens to that one little photosynthesis box that they mentioned. So a lot of the energy actually goes into building the tree. One molecule at a time, one atom at a time. And what never ceases to amaze me is that nature is able to build itself at ambient temperature. We talked a lot about the embodied energy in building PV crystals. That stuff's got to get hot. Whereas with nature, it never ceases to amaze me just that all of this kind of happens at ambient temperature. Okay, some of that energy is the energy that's not used as photosynthesis, as actually growing the organism. Some of it is radiated as heat. We talked about with our first couple problems in solar thermal that whenever there's a temperature difference between two bodies, radiation occurs. Heat transfer also occurs through convection and conduction, but this is showing that the radiation is moving away from the tree. Also evaporation. In 101 we talked a little bit about the latent heat of evaporation, how much it actually takes for a molecule sitting there in a liquid state to then be evaporated in a gaseous state. That's basically where the energy goes into making that molecule more mobile. Okay, so these are plant systems. Obviously, the animal is also storing organic energy. It's metabolizing plant matter, making its own waste. There's a whole section on bio-waste, and then of course it's radiating as well. And I think that what they're just trying to show with the root system is that there's energy flow underground as well that we can't necessarily see. All right, so keywords in 4.1, biomass. That's anything that's recently living. So you wouldn't call coal biomass, for example. There's a paper we're going to explore later in this chapter that was sent to me where biomass writ large, coal, oil, natural gas is all sort of ancient biomass. But for the sake of this chapter, it's just recent, something that's grown more recently. Anything living in there is called the biosphere. More or less anywhere you'd find anything alive. We just talked about photosynthesis. We've talked a lot about metabolism. We spent a lot of time on that in 101, talked about the fact that humans need 10 megajoules per day. And that ends up being about 100 watts. You could do the same thing for any of these organisms that we're looking at on the screen right now. Just mentioned evaporation. And I'm starting to see this next practice become more popular. The word humus is mentioned as well as peat. Humus is just kind of wood or any other plant matter that's on its way to becoming soil. You can think of it a little bit like, I don't know, mulch. Okay, so the next thing that's mentioned is the fact that these things can be turned into fuel. Oh, this little, not sure where this guy came from. I guess this is new. It's not in this particular textbook. You don't see this in your textbook, do you? Is that? Oh, there it is. Huh. Okay, it just kind of skipped over. Sorry about that. I guess what I was trying to get to is the fact that all of this energy obviously can be turned into fuel. Traditional biomass is mentioned, so there's firewood, rice husks, other things that otherwise would be wasted. That's traditional biomass. It could also be burned for electricity generation. Biofuels are mentioned, so charcoal is one, biogas, bioethanol, biodiesel. So these are things that are made from biomasses rather than fossil fuels. And then there's a whole new thing. It says in recent decades, terms such as new modern bioenergy have come into use. So this would be, say, algae, for example, something that you wouldn't typically, that would be purpose grown. That would sort of be an example of new biomass. Okay, now let's look at some numbers. I like this box 4.1. Box 4.1. Total mass of living matter. So what are we looking at? 1,800 billion dry tons. I know for a fact that in Montana there are 150 million dry tons of timber standing right now from the beetle forest. So a lot of what I'll do is take this, and you can turn this directly into an energy conversion, and we'll do that a little bit later. But and this is always a little bit surprising to me. This is the total mass in the oceans. There's only 4 billion dry tons. So relatively empty. There's the world population listed there. We're close to 7 billion. We'll look at that a little bit more in chapter or in summary 3. Here's the energy stored. So they've already done the conversion for us. They've taken that number of dry tons and looked at energy stored. Stored in biomass. And we're looking at 25,000 exajoules. And we can kind of turn that into a sustainability question. So if all of that biomass energy were to be turned into primary energy, let's see, 25,000. I get enough zeros? Yeah, 25,000 divided by 500. So there's a 50-year supply of biomass sitting on the planet right now. And the net annual production, so that's basically how much is grown, or what fraction of the photons that hit the planet are actually turned into biomass. 13 billion dry tons. Let's look at that one too. I want to look at that in terms of sustainability. So let's just say dry tons per year equals 30 billion dry tons per year. How can we determine if that's actually keeping up with production? We actually need to turn that into exajoules. Any idea how to do that based on what I just showed you? Little math problem. Let's do it this way. So if I know that 1,800 billion dry tons is equivalent to 25,000 exajoules. And I know that we consume 500 exajoules. This is going to have this is going to play out when we read that new summary paper that I just found. This should basically tell us how many, the equivalent of how many billion dry tons we use each year, right? If we just do that little one equation, one unknown. So let's do that. I'll pop into Microsoft Excel. So I'll just do it in one fell swoop here. So equals 1,800. Make this a little bit bigger so you can see it. So I'm just going to do 1,800 times 500 divided by 25,000. 36. So that basically means we consume the equivalent. If we were to get all of our energy from biomass, it would be the equivalent of consuming 36 billion dry tons. Does that sound a lot or a little? It's tough. I mean, it's 5 tons per person. Like, okay, here's your 5 tons of that. It actually doesn't seem like a whole heck of a lot when it comes down to it. Like, I can't. Maybe it's just because that's the average. That's what the average human consumes. North Americans are at 6 times that. But if we look at those two numbers, the 36 that I just showed you and the 130 basically means that nature is replenishing biofuel on the planet 3 to 4 times faster than we are currently using it. See what I just did there? So I know that there's 1,800 billion dry tons on the planet. That's the equivalent to that much energy. So I just kind of looked at our annual consumption rate and came up with 36.
But that's also because most of our energy is coming not from biomass, but from, well, previous editions of biomass, coal and oil and stuff.
Yeah.
Right now, that's our supply. If we were actually to get rid of those and start using that, start using biomass, we might use more of it.
Yeah. Well, it's funny too, because it actually says right here in the book that we actually are going through biomass at a rate of 50 exajoules per year. Oh, okay, that makes sense. 1.6 terawatts. And you can convert that into dry tons as well. Okay. All right, so bioenergy past and present, 4.2. Let's see how we're doing on time. Yeah, we're doing fine. Okay, so 4.2, bioenergy past and present, from wood to coal. And when I was just at this, I was at a clean coal conference there in Billings last month, and what was pretty remarkable is they were just showing sort of over time where we get our energy from, and it was just in terms of a percentage. So here's 0, and here's 100%, and it was something kind of like this, where all of this stuff out here was wood up until you hit 1860 or so. It was almost all of our energy was go back to the the Romans, the Chinese, the Greeks, what have you, and that's where it came from. And really just for heat and for cooking. Furnaces are mentioned here for using charcoal. And obviously by the time we were looking for newer technologies where higher temperatures were required, that's where we moved away from wood and now into what's called coke, which is part of the coal process for refining metals. It does mention here that the increased demand for coal to refine metals, etc., led to deeper mines, the need to pump water, so there's even more energy. And so you can sort of see this sort of feedback loop occurring where the faster you want to get raw materials out of the ground, the deeper you have to dig, more steam is required. The steam, of course, is being made by coal, and on you go. Okay. And then their next question, it says, will the 21st century see the reversal of this process, basically going away from coal and more back to biomass? It should, and then it says the data in 4.1 that we just reviewed shows that this is theoretically possible, since the annual energy in biomass is approximately 5 times the world primary consumption, as we just said. I guess I was looking more at 3 or 4. However, there are many practical and economic factors that may limit this. And are we going to need to get all of our energy from biomass? No. We've already discussed solar thermal. We've already discussed photovoltaic. We're going to get into many others, but it's a potential contribution. Okay. As mentioned, the range that we're looking at in terms of harvesting is 40 to 60 exajoules. And I want to show you something else that is just astonishing to me. We can sort of look at sustainability. I don't know if you've ever seen this picture or not, but if we look at Haiti and the Dominican Republic, they're on the same island. And so we were just mentioning like how sustainable is biomass as a resource. Well, if we take a look at the Google Earth, and unfortunately, oh no, it's right there, it's still there. So this is the political boundary right here that you see. And if we start to zoom in, and if you focus right there, it's green on one side and not so much on the other. Haiti has very, very poor forestry management policies. They've cut down forests at the rate that they've actually lost a lot of topsoil. They're making charcoal and what have you, but at a rate that's just unsustainable. I couldn't believe it the first time I saw it, but like right there, I mean, it's just almost literally night and day. You move along the border and see how one country has had much better success, and and really as a result, better economic success too as a result of their forestry practices. If you get a chance, you might read Jared Diamond's book Collapse. He talks a lot about how Japan's forestry practices actually saved their economy in a lot of ways. They could have ended up in a similar situation. So, and if you want to get into this topic deeper, there are several forest economists at this university. Look at that. Okay, so 40 to 60 exajoules. It's mentioned that biomass is the fourth largest source of energy, at least 10% of total consumption. But, as mentioned, up to 90% in some of the poorest countries such as Uganda. And this continues to rise. The question is, can we do it in a sustainable manner or not? 10% of primary energy in China, 35% in India. There's another one too. Advanced systems for domestic heating, district heating, and I see that coming on in a big way. District heating through our existing infrastructure, where you're actually, rather than exhausting heat up into the atmosphere, it's actually stored underground and pumped and moved around in a more sustainable way. Combined heat and power have helped Sweden towards a 5-fold increase in the use of bioenergy since the 1980s, reaching nearly 50 gigajoules per head of population. And I don't know if they count their other waste energy practices in that too, but it's pretty impressive what Sweden's been able to do. Okay, I'll take a quick break there and then we'll get into some chemistry.